Hello. I'd like to discuss the relationship between the force of gravity on the moon and that on the Earth. We are told that the moon has a force of gravity on its surface that is only 1/6 that of the Earth. I'd like to briefly discuss why that's so. Now, in order to discuss gravity, we need to use the universal law of gravity shown here. The force between two objects is equal to the universal gravitational constant times the mass of the first object times the mass of the second divided by the distance between their centers squared. So let's imagine that the big M is a planet like the Earth or a moon such as our moon, and R would just be the radius because the distance between an object on its surface and the moon or the Earth's center would be the radius of the moon or the Earth. And little m is the mass of the other object. We could actually call this G times m, or if you like, m times G. So G would be, little g would be capital G m over r squared. Now, the radius of the Earth, if you look it up, a place like Wolfram Alpha, is 6.367 times 10 to the 6 meters. That of the moon is 1.7 times 738 times 10 to the 6 meters. So the moon has a much smaller radius than the Earth. And of course, the radius comes in the second power. So you might think, because it's an inverse square relationship, the moon would exert a greater force. But of course, there's the mass, and we know the Earth is much more massive. And although mass occurs only to the first power, whereas the radius to the second, that's a little misleading because the mass of an object really depends on its volume. And the volume of a sphere depends on the radius to the third power. So the mass of the Earth, or the moon, is equal to the average density or the mean density of the Earth or moon times the volume of the Earth or moon. And the volume is 4/3 pi r cubed. So if we substitute for mass, rho, the density, times 4/3 pi r cubed into this formula, we get the force is equal to G times the mass of the Earth or moon, rho, 4/3 pi r cubed, divided by r squared, times the mass of whatever object is on the surface. Now the r's, if we cancel the r's, we see that the r cubed over the r squared gives you r. And so the force of gravity actually, for a body like the Earth or the moon or Saturn or what have you, depends on the first power of the radius. And it also depends on the density. Okay, if we rearrange these terms, we get 4/3 pi g rho r times the mass of whatever little object is on there. So the force of gravity on the surface of an object, like a planet or a moon, is proportional to rho, the density of that object, times r, the first power of the radius. And the g, of course, would be this quantity right here. Okay, so let's see what we get. If you look up the density, the mean density of the Earth, you get 5.515 grams per cubic centimeter, and you can turn that to kilograms per meter because we want to work in SI units. The density of the moon is 3.344. These are mean densities, 3.344 grams per cubic centimeter. The gravitational constant is the universal gravitational constant, 6.67384 times 10 to the minus 11 meters cubed per kilogram per second. So if we substitute for little g, the acceleration due to gravity, for the surface of the Earth, we use capital G times the density times 4/3 pi times the radius. And we plug in and look at the units. force is equal to 9.816 using these units. Meters per second, it should be squared. Meters per second squared times the mass of whatever object is falling on the Earth, like a baseball or what have you. It will accelerate at 9.8 meters per second per second. Do the same thing for the moon. Same gravitational constant, a different density, and a different radius, and we get 1.625 meters per second squared times the mass of whatever object, the same baseball. It's going to accelerate much more slowly on the moon. And if we take the ratio of the force on the Earth times the force on the moon, we would divide the gravitational acceleration, I'm just going to report it to two places, 9.8 meters per second squared, divided by 1.6 on the moon, meters per second squared, and we get about 6, a factor of 6. So this is a little exercise in verifying that the Earth exerts a gravitational force which is 6 times greater than that on the moon. I think a lot of students and a lot of people think that it's all due to mass. And really, both factors come into play. The mass and the distance between them, and if you factor out the distance between them, the gravitational force is proportional to the radius to the first power, and in that it's also proportional to the density of the object. So the Earth has a greater gravitational force than the moon because it has a larger radius and because it has a larger density. Okay, thank you for your attention, and I'll see you next time.